In this next unit, we're going to talk predominantly about quadratic functions, but before we can do that, we need to start with complex numbers. So far up to this point, we've been dealing with real numbers. So that's our counting numbers, irrational numbers like square root of 2, but something that's real. So what I want to do to introduce the idea of a complex number is to think of the graph of y equals x squared plus 1. If you were to graph it using our transformations from the last unit, this plus 1 just moves that square function up 1. So we have this kind of shape right here. So if you notice, this graph never touches the x-axis. And anytime we're solving for x-intercepts or y-intercepts, you're setting something equal to 0. So in the case, if you want to see if this actually crosses or touches the x-axis, this would mean your y value is equal to 0. So because this does not touch it, we have no real solutions to x squared plus 1 equaling 0, which is exactly the same thing as saying if I take x squared, it's never going to equal -1 for a real number. Because think, if you have a positive number, like 1 squared is 1, -1 squared is still +1. I will never take a number, times it by itself, and get something negative for real numbers. So this is why the imaginary unit needed to be defined. And so what this is we use the letter I to indicate something imaginary. So it has a very specific definition. It is the solution to this equation. So our imaginary unit I is defined by the square root of -1. Or another way to think that, if you square both sides, I squared is equal to -1. Okay? So this gives us a way to talk about solutions to something that doesn't have a real number solution, but still has a solution in this complex plane. So our complex numbers are really just a combination of the imaginary unit and then some real number as well. So if we say a and b are real numbers, then any number that has the form a plus bi is a complex number. And so this is specifically written in standard form. Just to give you some examples, like 3 plus 7i is a complex number. -9 minus 2i is another complex number. But standard form just allows you to immediately see what we call the real part. So it's the part that's just the real number. And then we can also immediately see the imaginary part, which is the thing that's attached to the I. So standard form has these two fully separated. So I immediately know the value of A and I immediately know the value of B. Okay? So one of the things that's going to pop up pretty frequently for us is when we talk about using division of complex numbers, we're often going to need something that's called the complex conjugate. And so if we have a complex number, a plus bi, its conjugate is given by just changing the sign of the imaginary part. So as a quick example, if I have the complex number z as 4 minus 7i, its conjugate, we use a bar to just denote that. You keep the numbers exactly the same, but you change the sign on the imaginary part. So its complex conjugate would be 4 plus 7i. So complex numbers typically are going to come into pairs. When we talk about solving equations, you're going to see it's going to be a complex number and its conjugate as solutions to that. And then some really nice stuff happens when we take a number and multiply by its conjugate. So let's try a couple examples. Let's get some familiarity with putting something in standard form. So I'm going to take a long time to do this first problem, but pretty much anytime you see a minus sign under a radical, immediately it's going to turn into an imaginary number. So if I go to simplify this, using our properties of square roots, we can write -25 as 25 times -1. And then from there, remember, we can take the square root of each thing individually. So it'd be the square root of 25 times the square root of -1. Square root of 25 is 5, and then this piece here, the square root of -1, is exactly what our unit I is. So this simplifies into 4 minus 5i. So honestly, at this point, you can just jump right to this. Whenever you have that minus sign under the radical, pop it out as an I. So let's do this example. I have the square root of negative 49. So I'm immediately going to take out that minus sign, and it becomes square root of 49i. And then we'll divide by 2. And then the square root of 49 is something we can actually do. It is 7. So we end up with this. Now, technically, this is not fully in standard form because I don't have the separation between the real part and the imaginary part. So to put this fully in standard form, just take each piece and divide it by 2. So now you can immediately pick off that the real part is 3/2. Don't know why I have that extra minus there. And then the imaginary part is 7/2 times I. When we deal with operations involving complex numbers, honestly, not a ton changes. You can treat I like a variable, just know it has a specific definition. When I'm working on combining stuff, I can only combine like pieces. The other thing I would highly recommend is that anytime you see the square root of a negative number, turn it into an I. Don't try to simplify stuff to start with. So for this first problem, I want to take one complex number and subtract it. And remember, when you subtract something, really you can just distribute that minus sign to both pieces. So this turns into plus 10 and plus 2i. And now when I combine these, I want to combine the like components. So I have 5 plus 10. I can definitely combine the two of those. That becomes 15. And then we have 7i plus 2i. We can combine those as well. And in total, we have 9i. Okay. And then this is in standard form, so we're all good. We can immediately see the real part is 15. The imaginary part is 9. When we work on multiplying two complex numbers, you're just using that FOILing process. And again, treat I like a variable. So when I go to multiply the first pieces, that gives us -3. When we do the outer, this gives us plus 9i. Then doing the inner gives us plus 2i. And then finally, the last would give us -6. And when we do I times I, we get an I squared. Okay. So from here, we can do a little bit of condensing. So that's -3. The 9i plus 2i we can condense to 11i. And then I want this to be a complex number in standard form. I squared is nowhere in my complex number. So this is where we use our definition that I squared, remember, is equal to -1. So I can replace I squared by -1. So this really gives us -3 plus 11i, and that turns into plus 6. And then we can do a little bit of condensing. -3 plus 6 gives us 3. So fully in its simplified form, this turns into 3 plus 11i. For this next one, this is where it's going to be important that I would highly recommend turning everything into i's first. So right off the bat, both of those have a negative. Pop out that minus sign as an I. So we have root 17 times I, and then we're going to times that by root 17 times I again. So when we do multiplication, we can combine the square root of 17 times the square root of 17. Really, that gives us the square root of 17 squared. And then when we have I times I, that turns into I squared. So for both of these, when we take the square root of 17 and square it, it cancels. And then again, I squared is -1. So this is the same thing as 17 times -1 or -17. Okay. So it's really easy within here. to do some stuff that breaks rules, so just be careful. Like I said, anytime you have an I, turn it into an I before you start dealing with the radicals and everything left over. So let's try a couple more. The next two are going to be a little bit different, but for this first one, we're just doing division. So immediately on both of these, I'm going to go ahead and I'm going to pop out an I. So we got root 70 times I, and then root 10 times I. And then luckily enough, we have I divided by I, so those cancel each other out. And we're left with the square root of 70 divided by the square root of 10. And if you remember back to our properties, we can write this under a single radical as 70 divided by 10. So this ends up becoming the square root of 7. Now these next ones are very different because I have I raised to a power. And I want to be able to write this just as a complex number. So it should have I to the first power, maybe times a constant, plus a constant, something like that. So with these, you're going to have to do some kind of breakdown. So for this first one, what I want to do, I have I to the fourth. The only thing I know about with I is I and I squared. Those are the only two things we know what they are. I is the square root of -1, and I squared is exactly -1. So I'm always going to try to break down I to a power utilizing one of these. So thankfully, when we have I to the fourth, remember we can break that down as I squared times I squared because we would go ahead and add these powers together. And I squared is -1, so this is -1 times -1. I to the fourth ends up simplifying down to +1. Okay. What I want to do is I want to look at this a different way because it's going to be more beneficial in this next example. What we can do, because it's an even number, is we can write this as I squared to the second. Because in this case, you would multiply these two numbers. And then that I squared in the middle, we can replace by -1. So this is -1 squared or +1. Because for this next one, I don't want to have to write I squared times I squared times I squared until I figure out how many I squareds I need to get to I to the 19th. What I can do is I can always turn an even number of them over using this process. But since we have an odd number, what I'm first going to do is I'm going to break this down as I to the 18th times I, because it's I to the first power. So again, this is like there's a 1 here. You would add these two exponents, and that would give us the 19th power. Right? Now, this I to the 18th, I can break down even more. So we can write this as I squared and then raised to the 9th power, because we would multiply those two exponents together. So I to the 18th we can write in this way, and then it'll be times I. And again, I know what I squared is, so this is -1 to the 9th times I. And then -1 to an odd power is -1. So really, I to the 19th simplifies to -I. Really, anytime you have I to a power, it's going to reduce to 1, -1, I, or -I. So that'll be I to a power. It's going to be one of these four things. So again, try a ton of examples. Try to see how many I's can you turn over using I squared, and then what gets left over from there. So we have one last example that we're going to go through, and that's going to be working with a quotient. So what do I do when I have a complex number divided by a complex number, and I want to put this in standard form? So when this happens, this is where our conjugate is going to come into play. So what I'm going to do is I'm going to take this expression and I'm going to multiply by the conjugate of the denominator. So when we're dealing with our conjugate of 9 minus 3i, remember all we do is we change the sign on the imaginary part. So this becomes 9 plus 3i. So to simplify this expression, what I want to do is I want to multiply the bottom by 9 plus 3i. But I can't just do that in the bottom. I've got to keep this expression exactly the same. So I need to do the same thing in the numerator. So ultimately, we're going to have two foiling processes that we have to go through. So I'm going to start with the bottom just so you can see why we multiply by the conjugate. So when we multiply the first terms, that gives us 81. When we do the outer, that would be 27i, and it's positive. When we do the inner, it's minus 27i, which is really nice because those cancel each other out. And then when we do the last terms, negative 3 times positive 3 is negative 9, and the I times I gives us I squared. So in the process of multiplying by the conjugate, we get something that's going to simplify really nicely. Okay. Now, unfortunately, in the top, the same is not going to be true. So if we do 9 times 7, that gives us 63. 7 times 3i gives us 21i. 9 times 4i is 36i. And then last but not least, 4i times 3i gives us 12i squared. Okay. Now it's a matter of cleaning stuff up. So on the top, we can go ahead and do 21i plus 36i. So that leaves us with 63 plus 57i. And then also, remember I squared we can replace by negative 1. So this is 12 times negative 1. And in the bottom, we're left with 81. And 9i squared, we can replace the I squared by negative 1. Okay. So just for room's sake, this becomes 12 times negative 1 comes minus 12. And here, negative 9 times negative 1 turns into plus 9 in the bottom. So if I take 63 and I subtract 12, that gives us 51 plus 57i. And then we have 90 in the denominator. Okay. And now again, I got to put this in standard form. This is not quite done. So I need to break each of these as 51 over 90 plus 57 over 90i. And then really all of these are divisible by 3. So I'm going to take the top and divide it by 3, the bottom divided by 3, and that's going to give us 17 over 30. And then same thing, we're going to divide this by 3, and we're going to divide this by 3. And that's going to give us 19 over 30i. Okay. And that is as fully simplified as we can make it, and we can easily see what the real part is and what the imaginary part is. So again, these are going to pop back up in a couple sections when we start going through quadratic equations. So we're going to see we don't always have real solutions, and imaginary numbers can indeed pop up there.